Hello students, how are you? How is your preparation going on? So today our topic is thermodynamics. Now, can you guess what does it deal with? You will see in thermodynamics it is consisting of two words, thermo and dynamics. Thermo is something to do with heat, and dynamics, this word you have studied, well, we have basically studied mechanics. And mechanics basically deals with what? With nothing but mechanical energy, right? Energy, work done. So here, basically, we will deal with work done. That is, how heat and work done are related, or vice versa, work done and heat are related. And if there are or is anything more addition to it. Now, to study thermodynamics, we need a system, right, on which we are actually, applying heat, some work, it is generating some work. So that kind of system is we called thermodynamical system. Any a state of matter that is solid, liquid or gas can behave as thermodynamical system. But for our convenience and for our practical purposes, we choose gases to be our thermodynamical system. And we basically study all our laws, right, with thermodynamical system. In thermodynamics, you will find three laws. First one is definitely the first law of thermodynamics. Second is the second law of thermodynamics. And the third, actually there is no third law, but there is a Zeroth law. Zeroth law of thermodynamics. Zeroth law comes from the word zero. What happened? Like initially scientists, they proposed the first law and the second law. But the Zeroth law, finally, it is, when I'll say the Zeroth law, you will understand it's a very obvious thing. But in science, nothing is obvious. We need to formulate and we need to write it in a kind of law. So, as we have written a very obvious thing, which the concept which comes much more, which is a more preliminary concept than the first and second law. So, they wanted to put the word zero, so which is before first and, one and two. So, it is Zeroth law of thermodynamics. Let us see what is Zeroth law of thermodynamics. Zeroth law of thermodynamics says that if there are two systems, A and B, which are in thermal equilibrium with another system separately with C, that is, they are in thermal equilibrium, then these systems will be in thermal equilibrium to each other. What is the meaning of thermal equilibrium? Thermal equilibrium means that there is no exchange of heat. There is no exchange of heat in between these two systems. And when there is no exchange of heat, you know from your basic idea of heat and temperature that these systems will be in the same temperature. So if A and C, they are in the same temperature, and B and C, they are also in the same temperature, then definitely A and B will be in the same temperature. Same temperature and no heat flow. This is a very obvious thing. You can just equate it with some numbers and we know, so we have termed it as Zeroth law. But the useful one is the first law of thermodynamics. What is that? First law, before writing, you can understand when we'll write, it is nothing but a special variation of conservation of energy. In physics, you will see this is a basic law, conservation of energy, and it has lots of variations. right? So like that is interchange of mechanical energy, kinetic to potential, and there are many others. First law of thermodynamics is one such of them. What it states? It states, it's right like this: del Q equal to del U plus del W. Del Q is the heat given or taken from the system. Del U is the increase or decrease of internal energy. So del U is nothing but increase and decrease of internal energy. And del W is the work done by or on the system. So work done by or on the system. Del Q is the heat given. See, every time del is nothing but something is being added. That is, it is not a constant value. Something is being added or something is being subtracted. Del Q is the heat given or taken from the system. So when heat is given, it will be positive. Given. When it is taken, it will be negative. Del U, when it is increasing, it will be positive. When it is decreasing, it will be negative. Then del W, when the system is doing the work is done by the system. So by the system is positive, and on the system is negative. So negative work means we are doing work on the system. Okay. Now let us explain each and everything very slowly, clearly. First, we will see what is the nature of del Q, del U and del W. First of all, first let us try to understand this. Del Q is the heat. Suppose there is a gas, right? You are heating up the gas, that is, you are applying some heat on the gas. So what will happen? Two changes will occur. One, because of the heat, the molecules, they will start vibrating more vigorously. And you must have studied in the kinetic theory of gases, when its molecule starts vibrating vigorously, what happens? Definitely its kinetic energy increases, means its temperature increases, right? That leads to the change of the internal energy. Internal energy is nothing but the overall, the average kinetic and potential energy, of course, in the gas. And another thing will happen, that is, the gas will expand. Now when the gas is expanding means what? Definitely there is a force, that is, the gas have pressure. Pressure applied over an area is a force, and with that force the gas is expanding, so there is a displacement. So force into displacement, so some work is also being done. The heat is increasing, amount of heat is increasing its internal energy, as well as it is doing some work. Understood? Now let us try to understand what is the nature of all these things. You will see, as we are talking about the internal energy depends only on the temperature and also on the intermolecular distance between them, that is the potential energy. So these things are these things depends only, so these are dependent only on the point or the state, only on the point or the state. Now okay, before coming to other things, any gas is defined by three variables. Any state of a gas, three variables, that is the pressure, volume and the temperature. So pressure, volume and temperature, these defines the state. So now internal energy depends on temperature, so it depends only on the state. It is a state variable. but we will see work done depends on what path it is going, on what path this expansion is happening. What is the meaning of this? The gas can expand because, you know, in solid and liquid, there the expansion is very limited, but in gas, if there is no boundation, it can expand freely also. And it can, you know, a process called isobaric. Isobaric means when pressure is constant. So gas can expand when the pressure is constant. It can expand like when the pressure is having some other function, like not constant but some other function. Even the gas may not expand also. That is, which we call isochoric, when the gas is not expanding. In all the cases, work done will be different. So work done depends on the path. That is, if there are 2 points in the gas, say A and B, 2 points mean 2 state. Say here the pressure is P1, V1, T1. Here the pressure is P2, V2, T2. If we take the gas from this 3 separate path, we will see in these 2 states the internal energy change will be the same. That is, if this is U1 and this is U2, we will see in both the cases U2 minus U1, or rather UA and UB, we will see UB minus UA is constant. But the work done, right, WAB, we cannot just specify WAB, because WA to B, we have to specify whether it is through 1 or 2 or 3. So WAB1 may not be equal to, it can be equal to also, but mostly it will not be equal to WAB2 or WAB3, because work done depends on the path, the way the gas is being expanded. And if work done is different, then definitely del Q is also different. So I can write del Q to be also a path dependent function. Understand? We'll explain this with the help of a problem. Okay, let us see. I'll do a problem like this, very simple, similar problem. Say 2 states of a gas A and B, right? Initially, what is happening? That is, the heat given, right, is 400 joules, and the work done, say it is 100 joules, right? We have first what we have to calculate, that is del U. Now you know del Q equals to del U plus del W. Then definitely del U will be equals to del Q minus del W. It is nothing but 400 minus 100, that is 300 joules. So say in this path, the internal energy change is 300 joules. And internal energy change will remain the same, right, from A to B. But the second question is, this is del U AB. Now what will be the internal energy change when the gas, suppose it is in another path 1, 2, and this is taken from path B to A, that is, it is returning. Now with logic you can understand, if from A to B internal energy changes, that is, it increases by 300 joule, then definitely from B to A it should decrease. It should decrease by the same amount, right? So by analogy we can say it should be minus 300 joule. Let's try to go deep into this. Say we have taken a gas from A to B and then again from B to A. Now, so in a cyclic process, so as we have said that internal energy is a state dependent function. So as we are starting from A and again coming back to A, then definitely we can say UA to A should be 0. Now UA to A means what? UAB plus UBA, that is equal to 0. UAB equals to 300 joules plus UBA equal to 0. That means UBA will be minus 300 joules. It means what? That is, if we can say like this, that from A to B, if the internal energy increased by 300 joule, from B to A it will decrease by 300 joule. Got it? First, how to calculate this also is clear. Now the third question is, that is, say in a different path, the W work done in a different path, say 2, is 400 joules. Now what is the heat change? Now see, if work done on the system, and it is specified work done on the system, Now if it is said work done on the system, then this cannot be 400. This should be work done on, means it should be negative, minus 400 joules. And therefore del Q will be del U plus del W, and del U will be remaining same. It is nothing but 300 joules. That is 300 minus 400, that is minus 100 joules. So if del Q is now minus 100 joule, it means some heat is being taken from the system, not heat is not given. So the system is losing some heat. Losing heat. Understand? Okay. Now let us go deep into the work done thing. So like for work done, say work, force into displacement, right? So, or F into X, this is a very general formula. So when the force and the way the force and the pressure, it is shifting, it is changing, it is different for different displacement as it is varying. If we take a very small work done, del W will be nothing but F into dx, where F itself can be a function of X, right? So, and the force can be written as P into A into dx, right? Let us try to think of a practical situation. Say there is a piston, there is a cylinder, and there is a piston, right? It has some gas. The piston, this is the area A. Because of this gas, it is applied some pressure P, and the gas is also pushing it with the internal pressure P, and slowly the piston is moving from this place to this place, right? Let this be del X, right? So we can say the force generated is equal to P into A, and the work done is nothing but force into the displacement, that is P into A into dx. If we consider this not del X but dx, very very small, right? Then see, this A into dx is nothing but, A is a cross section area, dx is a displacement shifted by the piston, right? So this is nothing but the volume, that is dV. So I can write it is P into dV. So the work done can be written as integration of P into dV, where P itself can be a function of the volume. So basically, when we talk about the work done in gases or thermodynamical system, then we don't talk about force into displacement. We basically talk about the relation between pressure and the volume, right? Where pressure is a function of the volume. Because the thermodynamical state, or to define the state of a gas, what we define, what are the variables? That is P, V, and T. So we relate these functions. Now we'll try to elaborate on this, like how work is equal to P dV, how it is different for different processes. See, we'll have 4 basic process, and there can be innumerable other process. Say, first process is isochoric process. Isochoric process means, isochoric means when volume equals to constant, that is del V equal to 0. Then it is isobaric process. Isobaric process. Isobaric process means when pressure equals to constant, right? So no change in pressure. 3. Isothermal process, when temperature equals to constant, that is no change in temperature, right? 4. Adiabatic process. Adiabatic process, I think this is a new term, where the exchange of heat, there is no exchange of heat, that is a heat content within the gas is constant, that is no exchange of heat. Got it? We'll try to explain each of this process and how it is affecting the work done, and also the del Q and del U, all the variables, all the points for these process, and there can be some other processes too. See, for isochoric process, what I said, the volume remains constant, means del V equals to 0. If del V, change of volume, if itself it is 0, what will be the work done? Work done is nothing but P del V. It must be 0. So when work done in an isochoric process, when the work done is 0, what will be the heat? The heat will be nothing but the total internal energy. That is, in an isochoric system, when the volume is not changing, the total heat will just increase the internal energy. That is, change in heat will change the internal energy. Got it? Now we have isobaric process. We have isobaric process. In isobaric process, what will happen? Their pressure remains constant. When pressure is constant, now see, we have W equals to, for work done, what we have calculated, it is P dV. The P is constant, right? This P is constant, this P is constant, which is nothing but capital P. So we can take P outside and let the volume is changing from V1 to V2, that is V1, V2. That is, P becomes nothing but V2 minus V1. So work done is nothing but P V2 minus V1. So here what will happen? Del Q will be del U, plus obviously this is the work done, that is P V2 minus V1. Isobaric process. Now we are coming to isothermal process. In isothermal, T is constant. Now when T is constant, temperature is constant. I have told you internal energy depends on the temperature. So when del T, that is no change in temperature, so definitely del U will also be equal to 0. So what will happen? Del Q, del U portion is 0, is totally del W. Del Q will become totally del W. There is an isothermal process. The whole work, whole heat will change in to increase the work done or to change the work done. Now, what is that function, or what is the value of the work done? Let us try to calculate. See, in a gas, in an ideal gas, PV, right? PV equals to, it follows the ideal gas law, equals to nRT. Now, PV equals to nRT. Now, when temperature is constant, so we can write PV is constant, right? So we can write P in terms of V, that is nRT by V, right? So we can calculate the work done, the value of work done, P dV, say V1 to V2. The value of P is nothing but nRT by V dV V1 V2. That is nRT comes outside, it is V1 V2. It is 1 by V into dV. Now 1 by V dV integration is nothing but log to the base E, that is, right, or it will be log V2 minus log V1, that becomes log V2 by V1. And as you know, PV equal to constant, it means what? P1 V1 equal to P2 V2. So V2 by V1 is nothing but P1 by P2. So we have to multiply this nRT. So it will be nRT log to the base P, P1, P2. Okay, fine. And del U is 0, del Q will also be equals to this. So del Q we can also write del Q nRT log V2 by V1. Now finally we are coming to adiabatic process. In adiabatic process, very interesting, del Q is 0. So there is no exchange of heat. Now in the first equation, if del Q equals to del U plus del W, and this itself is 0, it means what? 0 equals to del U plus del W. So del U equals to minus del W. Okay, what does this mean? First, let us try to understand. Work done, del U equal to minus del W. So if its work is done by the system, that it is positive, then internal energy becomes negative. Means internal energy decreases. What does this mean? That is, it is using up its own internal energy because there is no heat supply. So it is using up its own internal energy to do the work, right? So it is expanding, using up its own internal energy. Whereas if work is done on the system, that is, this is negative, then negative becomes positive, its internal energy increases. So if we do the work, that if we press a system, we decrease the volume, right? Then what will happen in internal energy? Because number of collisions, number of striking rate will be increasing. So what will happen? It will increase the internal energy of the system. Got it? So work done on the system will increase the internal energy. But what is that value of work done? You will see in an adiabatic process. Okay, I forgot that sheet, that previous sheet. Yeah, I forgot to say in the isothermal process, we also need to understand another thing. That is, what is a graph? In an isothermal process, the graph will be PV is constant. The graph for this will be like this, right? PV, this is isothermal. Whereas in the adiabatic process, we will see PV to the power gamma equals to constant. Now what is this gamma? Gamma I'll explain. Gamma is a value which is the ratio of Cp and Cv. Now what is Cp and Cv? Cp and Cv are the molar specific heat for constant pressure, and this is molar specific heat for constant volume. We'll come to it, and gamma is the ratio between them. And usually for Cp and Cv for monoatomic gas, the gamma is 5/3, right? And so it is PV to the power gamma equal to constant. It's not PV equal to constant. So now we will use this formula to find out the work done. Now we know, again, W equals to P dV. This is V1 to V2. P we can write, say it's a constant, K by V to the power gamma, it is dV, V1, V2, right? After integration I'm not doing, you will finally see it can be written as P2 V2 minus P1 V1 by 1 minus gamma, work done. Or see, P2 V2 is nothing but nRT2. Always remember, this equation can be different, PV to the power gamma equal to constant, or PV equal to constant, or depending on the, but the ideal gas equation, that is PV equal to nRT, this is always true. So in an adiabatic process, when the state is P1 V1, right, at 1 P1 V1 T1, at 2 it is P2 V2 and T2. So P2 V2 we can write nRT2, and this is nRT1, 1 minus gamma. So work done equals to nRT2 minus T1, 1 minus gamma. Got the point? Okay. And in this case, when PV to the power gamma equal to constant, you will see the graph between P and V, like in isothermal we got the graph like this. In PV the graph will be much more steeper. So this is PV to the power gamma equal to constant, this is PV equal to constant, right? This is for adiabatic, this is for isothermal. Now, why we need these graphs? Graphs, see, graphs can actually determine what is the work done. Say this is pressure, this is volume. Let's go back to all these things. When volume is constant, means what? The graph will be like this, right? When pressure is constant, the graph will be like this. Pressure is constant. Now see, when the pressure is constant, say we want to calculate what is the work done between V1 and V2. So V1 and V2, see, it is nothing but this P into, when pressure is constant, what is the work done? It is P into V2 minus V1. It's nothing but the area under the graph. Similarly, for isothermal also, if the volume increases from V1 to V2, this is pressure. Don't get confused. This is not volume decreasing. Volume is increasing, but pressure is decreasing here, right? Here also, the work done is nothing but the area under the graph. Similar, if it is an adiabatic process, the graph will be steeper. This will be also, the area under the graph will be this. Understand? Okay, now say there is a cyclic process. There also, area bounded within the graph, within this PV graph, will be the work done, right? But the internal energy change, there will be no change in internal energy, right? And the whole del Q will be converted to the work done. Okay. Now, yes. Now let us try to get into the what is the meaning of CV and CP, CP and CV. Now see, C, by the word C we say it is nothing but molar specific heat, right? It is molar specific heat. For molar specific heat means what? Heat per unit mass per unit change in temperature. When we say about molar specific heat, it is nothing but change in internal energy, right, per unit, per mole, per change in temperature, right? So now that is change in internal energy per mole per unit change in temperature. Now see, very interestingly, we are talking about isothermal. When isothermal T equal to 0, so del T equals to T equal to constant, so del T equal to 0. So if we try to find out the molar specific heat at constant temperature, it will be infinity. Whereas, okay, a molar specific heat for heat, let me make it del Q. That is heat per mole per increase or decrease in temperature. For adiabatic, Q equals to 0. So as del Q equals to 0, C adiabatic or CQ will be 0. So the molar specific heat of a gas is not constant as in liquid and solids. It can vary from 0 to infinity depending on the process or the path we are taking. So we just to specify this thing, we chose two things, CP and CV. CV is when the volume is constant and CP when the pressure is constant. Now when the volume is constant, that is the isochoric process, you must be remembering for isochoric, del Q, del W is 0, del Q is del U. So CV can change to del Q equals to N del T, will change to nothing but del U N del T. And for CP is nothing but del Q N del T, right? Where del Q is nothing but del U plus P del V N del T, del U plus N del T plus N del T. This is nothing but CV, and P del V by N del T, right? PV equal to nRT, R equals to PV by NT. This can be written as CP equal to CV plus R. It needs more explanation. We don't have so much of time, but just remember CP is more than CV by R, by the gas constant, right? So and for monoatomic gases, basically we have CV equals to 3 by 2R, CP then definitely it will be 5 by 2R, and gamma, which is nothing but CP by CV, it is 5 by 3. Okay, this is more or less on the theory matter of thermodynamics. Let us solve few problems. See, a very interesting problem. It came in JEE 2000. Starting with the same initial conditions, an ideal gas expands from V1 to V2 in three different ways. The work done by the gas is W1 if the process is purely isothermal, W2 if it is isobaric, and W3 if it is adiabatic. Then we have to say which one is true. Understand. W1 if the process purely isothermal. Now first, V1, V2, right, and pressure P1, P2. We have to first plot the graph, the PV graph, Now for PV graph, see, isothermal, as I was discussing, the change will be like this, somewhat like this. W2, it is isobaric. W2, isobaric means when the pressure is constant. So definitely this will be the graph of isobaric. And adiabatic, the slope will be more steeper. See, this end point V1 and V2 are the same. The gas is expanding from V1 to V2. One is isothermal. This is isobaric. This is adiabatic. Now we have to say about this. Now see, work done, you know nothing but area under the graph. Now see, area of 3 is less than area of 1 is less than area of 2. So area of 2 will be maximum, then area of 1, then area of 3. So this is the answer. Got it? One more question. Yes. As I was talking about Cp and Cv, what is the heat input needed to raise the temperature of 2 moles of helium from 0 to 100? Helium is a monoatomic gas, right? At constant volume. At constant volume, what is the heat? Constant volume, first del W equals to 0. So del Q is nothing but del U is nothing but N Cv del T, right? 2 moles. So 2 into Cv equals to 3 by 2 R. Del T is how much? 100. So it is how much? 300 R. We'll keep all the answers in terms of R, right? At constant pressure is nothing but, constant pressure means then we'll use not Cv but Cp. So del Q will be N Cp del T. N is 2. It is 5 by 2 R into 100. That is 500 R. And work done by the gas in B. Work done, what will be work done? Work done is nothing but del Q minus del U. Del U is nothing but the heat in at constant volume, which is 300 R. So it is 500 R minus 300 R. That is 200 R. Okay. Well, short of time, we'll do this last problem for today. See, the temperature of n moles of an ideal gas is increased from T0 to 2T0 through a process P equal to alpha T. Find work done in this process. Okay, first of all, pressure, the change in pressure with temperature is alpha T. Temperature, right, it's varying from T0 to 2T0. Okay, now there is no there is no variation with the volume. So what to do? See, we know PV equals to nRT, P equal to alpha T. So definitely in place of P, if we write alpha by T, V equals to nRT. So V we can write nRT square by alpha. Because see, pressure we know the function with T, alpha T. Volume also we need to have the function with T, because the work done is finally, work is nothing but integration of P dV, right? So P dV, now when we have the variables in P and dV, we can change it to T, and then the limits can be in T, T0 to 2T0. Now dV, V equal to nRT square by alpha. So what does this mean? nR alpha, these are constant. nR alpha, it is 2T dt, right? So now work done, what I can write then? In place of P we can write alpha by T. dV we can write nr alpha 2T dt, and the temperature is varying from T0 to 2T0. So T cancels out, alpha cancels out, nr and 2 it comes outside, 2nr integration of dt T0 to T0. Integration of dt is nothing but t. So 2T0 minus T0 is T0. It is nothing but 2nr T0. That is the work done in the process. So what we did in a nutshell, work done we know is integration of P into dV. P is given in terms of temperature. So from the ideal gas equation, we also change the V into temperature, and then we found the work done in terms of temperature. This is the first law of thermodynamics. You will get plenty of problems with first law of thermodynamics, mainly on graph, work done, CP, CV, all these things. Practice a lot of problems. This is a very scoring part. In the next topic, we'll go into the second law of thermodynamics. Thank you for today.